Hello dear students, welcome back to the tetrahedron chemistry classes and a very happy Diwali to you, right? And see, the various parts of the India are celebrating Diwali today, but in my region, we'll celebrate the Diwali tomorrow, that is on the 1st of the November. So I'm having the little leisure time to shoot this particular lecture, and that's why I'm ready with this particular lecture here. And this is my lecture number 4 on the polymer chemistry, and today we will discuss the elastomers or the rubbers. See, there is another class of the polymers which is known as the elastomers with certain other properties, and it's completely a theoretical part, but you need to learn all these things in order to write in your examinations as well, and in the competitive examinations as well you will find the question from these elastomers here, because these elastomers have the various applications. So by definitions, what are the elastomers? Elastomers are the polymers capable of being stretched rapidly at least of 150% of their original length without breaking and return to their original shape on the release of this particular stretch. This is the property. So those substances which have this property of stretching something about 150% of their original length. See, the properties are like that, very high tensile strength they are having, right? So due to this reason, when you release this particular stretch, right, then these elastomers regain their shape, whatever that's what I have written here. Okay, some of the properties of the elastomers are: elastomers should have the very high molecular weight of the polymer. That means degree of polymerization should be high, and to define what should be the exact value, you need to know the application of that particular rubber. Okay, and number 2, rubber must be cross-linked and the amorphous. See, your polymers maybe you are say semi-crystalline, the semi-crystalline form, in the amorphous form, various forms are there. But to characterize your elastomer, to characterize a polymer into a elastomer, the nature or the physical state must be amorphous. Okay, and there must be the cross-linking in the chains of the polymers, right? See, without cross-linking, it is not possible for an elastomer to stretch without breaking. So this cross-linking is very, very important, and there is a process to give the cross-linking to the polymer as well, right? And these polymers should have the very high flexibility of the chain. Definitely, when they have the high flexibility of the chain, only then you can stretch them without breaking. Okay, and number 4, the glass transition temperature of the elastomer should be very, very low, and the flow temperature should be as high as possible. So if you don't know what is glass transition temperature and what is flow temperature, for time being you can only remember this thing TG and TF as your flow temperature and glass transition temperature. In the later in the series, I will explain these things: glass transition temperature, flow temperatures, all these things with their applications as well. But right now, for the elastomers, it is enough to know that they should have the very low glass transition temperature and flow temperature must be as high as possible. Okay, and then the point number 5: your elastomers must stretch rapidly and considerably when stretched, reaching high elongation up to 500 to 1000%. Okay, this much of elongation must be there. Okay, so see there should be no confusion between the elongation and your stretching. So see, you're capable of stretch rapidly up to 150%, right? You can stretch them up to 150%, which give the elongation of the 500 to 1000%. So these two things are different. Okay, number 6, elastomers must exhibit very high tensile strength and very high stiffness when fully stretched. So okay, definitely when the tensile strength is very, very high, only then you can stretch it. Otherwise you cannot stretch it, and they should be very, very stiff also, right? Without stiffness, the strong bonding would not be there, right? And that's it for this high stiffness, right? Low stiffness actually will break the chain. Okay, and then you see natural rubber. What is the natural rubber and how we can get it? So this is the process of extracting the natural rubber from the tree. Basically, this tree is either the Hevia basiliensis, or your Hevia basiliensis, also known as the Gatta Parcha. And sometimes if you don't have the Hevia basiliensis or the Gatta Parcha Gatta Parcha tree, then you may use on the Bellata as well, right? So what you do, you actually cut this bark of the tree, which I have shown you here, and this liquid is dripping from that particular cut, and in the cone, V-shaped cone, or here it is not exactly the V-shaped, but generally in the V-shaped cone, you can collect that white material, and that white material contains the rubber. It is not actually the rubber, but it contains the rubber. It has a certain average composition. Okay. So the natural rubber is mainly extracted from the Hevea basilensis or the Gatta parcha and the Ballata tree. The rubber is obtained from the latex collected from the cut made in the bark of the tree. Latex is an emulsion. So this whitish color is the emulsion of polyhydrocarbon droplets in the aqueous medium and looks like the milk. It is not actually the milk, but it looks like the milk. The negatively charged particles of the polyhydrocarbons stabilizes this particular emulsion. So what is the region of the stabilization of this particular emulsion? The negatively charged polyhydrocarbon particles. What is the average composition of the latex? 60% of water is there, only 35% rubber is there. So you need to concentrate that 35% to the higher percentage, right? So after concentration, it may go up to 90 to 95%, right? And in the 3%, protein, enzyme, and the nucleic acid is there. Since it is the natural product, you are extracting this from the tree, so it's a natural product. Definitely natural product should have some proteins, enzymes, and the nucleic acid, which makes the 3% of that emulsion. And you know what is the source of the higher fatty acids? Only the plant material is the source of the higher fatty acids. So fatty acids and esters are 11% on it. You can smell this particular latex, then you will have the distinct smell from it, and that smell is maybe due to the presence of the esters in it. And in the 0.5%, or say in the remaining whatever the percentage, 0.5 is written here, whatever the remaining percentage is there in it, actually the inorganic salts are there, sodium, potassium, phosphorus, and all these things are there in this particular emulsion. So this is the average composition. So after average composition, you need to do the various processes of this particular latex to get the different kinds of the rubber. One such initial or the primary process is the rubber taping. So you need to tape the rubber. So rubber taping means basically rubber taping means actually the collection of these rubber particles and the increase of the concentration of this rubber. See, earlier I told you that only 35% rubber is there in the latex, but after this taping process, that concentration increases from this 35% to 90 to 95%. Please remember. So the milky white liquid latex is collected from the rubber trees in a cup by making a slight V-cut on the tree bark, as I have explained in my last slide. The collected latex is washed, filtered, and reacted with the acids, either acetic acid or the formic acid. If you don't have these two, then your salts like ammonium acetate or potassium acetate will also serve this process. Basically, this reaction will coagulate that rubber in the form of the rubber particles. So if you react that particular white material after washing, filtering, and all these things with these acids, so you will have your rubber particles, or right. So to coagulate the rubber particles here, and this crude rubber, basically these rubber particles are the crude rubber, and it consists of the 90 to 95% of the rubber. This is the main thing for you. 2 to 4% protein, it is not of very much of importance, right? Because you need rubber only, and 1 to 2% resins are also there in it, right? So this is the rubber taping process, which increases the concentration of the rubber in the emulsion. After that, you will do the creping of the creping means these basically it's a calendering process. It is a process like which you make chapati with the help of certain base and the roller on your hand. It is the process of like that only. You have calendering machine for this to this. Industries have generally, not you have, industries have. So if you want to know what is the calendering process, what is masticating processes, then you can Google them and you can watch the videos of various industrial process in the YouTube as well. Okay. So calendering is a process which is mainly performed to provide the shape to the rubber using the rollers. As I have explained, making of chapati with the help of the roller on the certain platform, right? So after but these calendering would done after the proper mixing of the chemical ingredients like sodium bisulfite. Sodium bisulfite is basically used to bleach the rubber. So you remove the undesired color from the rubber, you need the sodium bisulfite, and after that process you will do the calendering. That means you will convert those particles into the desired shape, whether you the circular shape or rectangular shape or the sheets, like all these things you will do. Basically the rubber passing through the after that you will see basically in the calendering process your rubber is passing through the creping machine. right? Creping machine is just like that, your chapati making system, right? With the help of the roller and the base, which converts the spongy or the rubber particles into the sheets having the roughness. See, if you see, you may have seen this crepe paper. If you touch the crepe paper, which used for the specific purposes, it has certain kind of the roughness on it. So those sheets actually, those rubber sheets, these rubber sheets are also having these roughness on their surface. So after, so it the rough due to this roughness, like the crepe paper, the rubber is also known as the crepe rubber basically. And this crepe rubber is also having the various applications. Okay. And then in the processing, see, first you did your tapping of the rubber, and then the creping of the rubber. After tapping, creping, you will do the this is you will now you will need a different kind of the rubber, which is known as the smoked rubber. So see, after converting into the different desired or the different shapes, you actually expose or you expose this rubber in the smoked houses, and smoke is produced either by the rubber or the coconut shell, which is the outer part of the coconut shell, by burning of the coconut shell, right? So this will give you the smoked rubber, which have the certain different properties from the crepe rubber. Okay, so smoked rubber is produced by carrying out the coagulation of the latex in the tanks fitted with the metal plates. So see, generally this here you have produced this, see, in the earlier process. If I go back, this crepe rubber, I have explained the process how you did it. But if you don't want this crepe rubbers, right, or simply what you can do, you can directly take this emulsion, right, and this emulsion you can directly treat into the you can directly treat that emulsion into the smoked rubber. So for making the smoked rubber, what you will do, see, this smoked rubber is produced by carrying out of the coagulation of the latex in the tanks fitted with the metal plates. After 15-16 hours, the tough slabs are formed. See, after this process, very tough slabs of the rubbers are formed. These slabs are passes through a series of rolling machines, right, like you did in the calendering process, and finally rubber sheets having the ribbed pattern are obtained. See, this ribbed pattern is very, very important. See, when you do the stacking of the rubber sheets, so this ribbed pattern will prevent sticking of the rubber sheet into each other, right? So you see here, the ribbed surface prevents the sticking of the rubber sheets with each other. These sheets are then dried in the smoke houses at about 50 degrees centigrade in the smoke obtained by the burning of the wood or the coconut shells. This smoked rubber is translucent in nature. What is the meaning of the translucent? Translucent means light can pass through this particular rubber sheets. However, the image would not be very, very clear after when light passes through this particular sheet, but it has the property that light can pass through this sheets. That's why it is translucent in nature. And sometimes it may have the amber color. So for you need to for this you need to know how actually amber colors look like. However, this amber color is not actually defining the any important application or the property, but this translucent nature is defining the very important application, right? And then you can see after that, okay, so this is the process. So see, in these past 3 or 4 slides, you have learned about how the processes by which you can convert the emulsion into the rubber. But now, what is rubber? Chemically, what is rubber? So rubber is basically your polyisoprene. So this is the isoprene unit. Isoprene unit, basically it is 2-methyl 1,3-butadiene. So if you want to write the IUPAC name, then I can write the IUPAC name as well for this one. IUPAC name is 2-methyl, right, but or buta 1,3-diene, right? This is known as the isoprene. When you polymerize this isoprene, so I am writing polymerize here. When you polymerize it, so what will happen? So this I have already drawn the mechanism. One of this double bond will break, and the one electron will shift here. So it will produce that active end, and one electron will come here, and by breaking this bond, this will shift on this terminal carbon, and this electron will shift here, will give you the one double bond in the center, and this will have the odd electron, this will have the odd electron, and then the polymerization continue at these two ends, and your polymer will form. So here you can see double bond C CH3, and N is the degree of the polymerizations. Okay, so this is basically your natural rubber, and natural rubber is your cis 1,4 polyisoprene. So if someone asks you in your Viva examination, what is the formula of the rubber? So you will say the polyisoprene. If the examiner asks what is the nature of this, what is the stereochemistry of this polyisoprene or the natural rubber, then you will say this is cis 1,4 polyisoprene. So what is the meaning of the cis? Cis means two identical groups will present on the same side. Please remember, this is something very, very important you need to know. That means this CH2 and this CH2, they present on the same side. Please remember, this is very, very important. Okay. And so this is the natural rubber. Properties of the natural rubber, very soft. It is very soft in nature and elastic in nature as well. Soluble in the carbon disulfide and the petrol, right? Because it is very, very soft, and it is the organic compound, right? So it is definitely soluble in the petrol and carbon disulfide as well. Okay, number 3, it is cis polyisoprene. That means the nature of this polymer is the cis, right? So what is the meaning of the cis? If you want, then I can write the configuration as well. Right, carbon, double bond carbon. Okay, so this is your CH2 and this is your CH3, and the polymerization will continue from here, right? And your hydrogen here, and then your CH2 and the polymerization would continue from here. So you'll find that CH2 and CH2 on the same side. This is basically the cis nature. Okay, I hope this is quite clear. So cis polyisoprene and thermally stable up to 82 degrees centigrade, right? So up to 82 degrees centigrade is stable. Due to the presence of the double bond, many chemicals can attack on it. You know that your alkene can do the various kind of the reactions. See, the electrophilic addition reactions are there. You can add acid to it, right? You can add say any electrophile, any substance which can produce the electrophile. You can react that double bond with that electrophile. So due to the presence of this particular double bond, which I have shown you in the previous slide, this natural rubber can be attacked by the many chemicals. So very limited application it is having. So you need to improvise its properties in order to use this rubber in the various applications. Okay, and you see drawbacks of the natural rubber. What are the drawbacks? Soft at high temperature and becomes brittle at the low temperature. See, if the temperature is very high, it becomes soft, and if you cool them down, if you cool it down, so it will have the brittle nature. And due to this, these two properties, the applications are very, very limited. You need to improvise or improve the properties. Number 2, it is too weak with a tensile strength of only 200 kg per centimeter square, right? So this is the kg per centimeter square is the unit of the tensile strength, and this tensile strength is very, very low. If you need that rubber in in the applications where you need to the 1000 kilogram per centimeter square, then you need to enhance the properties as well. Okay, so again, due to this property, this cannot be used everywhere. Number 3, it is attacked by the mineral oils, organic solvents, and also oxidized by the air and the acids. This I already told you, because it is containing the double bond, so many chemicals can attack on it, right? Number 4, it has the large water absorption capacity. Right, addition of the water in the double bond, you have seen this reaction in your class 11th as well. So due to the presence of the double bond, it can absorb water. Once it absorbs the water, then it may dissolve in the water as well. Okay, number 5, it undergoes the permanent deformation when stretched. That means stretching property. See, what are the elastomers of the rubbers? They have the very special property of stretching them, and if you release the stretch, then they regain their original shape. But that natural rubber is not having that particular property. If you stretch that natural rubber, it will undergo the permanent deformation. So these are the drawbacks, and due to these drawbacks, you cannot use this rubber everywhere. Okay, then there must be certain processing which will improve the properties of the rubber. So processes for improving the natural rubber properties, and one such very important property is the mastication. You can see this picture here, mastication. This picture shows the process of the mastication, right? So this is mastication. the rubber particles obtained from the tapping processes. Earlier you got the rubber particles from the tapping processes are still not ready to be used. When they are cooled, they are very brittle in nature, and when warmed, they become very gluey or the sticky, right? To remove the brittle nature and strong odor of the rubber. See, they have the very strong and the odor which irritates the human beings, right? So you cannot use this. So in order to remove these two very important properties, brittle nature and the strong stinking odor from it, you need to do the mastication of this. So in the mastication, it is allowed to pass through our rollers and it is pressed to make it the softer and flexible to work. Okay, we generally we have done in the calendering process as well. These CH2 linkage, right? This CH2 linkage links between the isoprene units in the rubbers are very weak. So this, as you see, this CH2 this bond is very weak, and on stretching this bond may break, right? If you put the mechanical stress on it, it may break actually. Okay, so what is the net effect? Basically the net effect is this big molecule will break into the small fragments, right? So you need to make this particular bond strong. How we can do this thing? Let us see. Compounding. Then when you will do the compounding of this one, so various compounding compounds are there, that means chemicals are there. One such compound, the picture I have shown you, this particular compound here. So like this, many other chemicals are also there for the compounding processes. So compounding involves the incorporation of the chemicals such as the plasticizers, vulcanizing agents. Generally the very important vulcanizing agent is your sulfur. Okay, and then stabilizers and the fillers. Definitely when in the raw rubber you do all the processes and you add plasticizers to it and you vulcanize it, right? And you add certain stabilizers and the fillers, then the properties will definitely enhance. And all these you can see these are the rubber pieces are there of the different colors, and these are obtained after doing all these processes, right? So these things need to be remember. And see, this is the thing actually. You see white fillers, then the carbon, your natural rubber sheets, right? All these ingredients, right? This is these are the processing aids. All softeners are there, and then this is the machine, right? And this will give you the various things. So this is just the picture. If you want, then you can see what is happening here. If you don't want this, then you can escape it, right? I don't know, somehow I forgot to remove this particular picture here. So if you want, then you can remove it. Now this process is very important, and in the examinations this question is generally there in your examination, which is known as the vulcanization of the rubber. And this vulcanization of the rubber is basically discovered by the great Charles Goodyear. So there is a tire company which is known as the Goodyear Tires. So however, the owner of that company is not the Charles Goodyear, but some other person is the owner of that particular company. But to honor this Charles Goodyear, which enhances the properties of the rubber for the application of the tires, that person actually named its company Goodyear Tires, right, after the name of the Charles Goodyear. So remarkable invention of self-taught chemist Charles Goodyear in 1839. So in 1839, Charles Goodyear actually discovered a very important property which is known as the vulcanization of the rubber. So here you see, this is the vulcanization. This is the very important invention of the Charles Goodyear, right? So what is the vulcanization? It is a method of compounding masticated rubber with the vulcanizing agents. It involves the heating of the rubber with the sulfur at around 135 degrees centigrade for 1 to 4 hours. Okay. Insertion of the sulfur in the rubber chains gives the cross-linking between the chains, which increases the tensile strength or the stiffness of that polymer chain, and then this gives the stretching property to the elastomers. Vulcanization improves the tensile strength, as I have explained, chemical resistance as well, wear and tear of the rubber. So this vulcanization process is so important for the rubber because it is giving the very high tensile strength to the rubber. It is also providing the safeguard against the chemicals, attack of the chemicals, and wear and tear as well. Degree of vulcanization depends on the application. So what amount of the vulcanization would be done on the rubber, it will purely depend on the application where you will use. For example, in the tire industry, about 3 to 4% sulfur and the filler like carbons are added for this vulcanization process in the tire industry. But if the percentage of the sulfur increase beyond 30%, full saturation of the bonds takes place, resulting in a very rigid, non-flexible rubber, which is called the ebonite. See, in your junior classes, say in your 7th or 8th classes, you definitely have done this charging process with the help of the ebonite rod. That ebonite rod is basically the kind of the rubber which have the very high percentage of the sulfur. Please remember, which is obtained, this ebonite is obtained by the process of the vulcanization. And this is the process. See, this is your polyisoprene, a rubber or elastomer, and this is another molecule, and this is the sulfur, right? And this is S8 basically, but for the simplicity, I have written S only. So when these two reacts basically, so these double bonds actually will break and they will form the cross-linking between the two chains. You see the sulfur is connected here and your sulfur is again connected here and sulfur is connected here. This cross-linking provides the very high tensile strength and resistance for the attack of the various chemicals as well. This is very, very important process and a very important question for your examination point of view. So this is monosulfide cross-linking in the vulcanization, because only one sulfur is connected between the two sheets. And then you can see here disulfide cross-linking may also be there, because see, once this is sulfur, these two sulfurs now are connecting this two. You know, sulfur is basically your S8. So you can do the mono sulfide. You can add one sulfide between these two chains. You can add two sulfides on it, right? So this is disulfide cross-linking. So 2 and 2. You see, this will increase the properties, right? And this is the complete picture. This is your rubber, and this is your S8 molecule, and steam you are passing. You are giving the pressure, and cross-linking is taking place. The trisulfide linkage are there. Okay. So these are the sulfur bridges. So in the examination, you can write only this particular sheet as well if you want, or these two are also equally good. If you want, these two reactions are also equally good for your examinations. Okay. And then you see the properties of the vulcanized rubber. After vulcanization, what will happen to the rubber? Very good tensile strength and the extensibility, right? The height, the tensile strength of the raw rubber was up to 20 kg per centimeter cube per centimeter square, 20 to 200, right? But for vulcanized rubber, it may jump up to 3000 kg per centimeter square. So this is the power of the vulcanization process, and that's why this Charles Goodyear did the remarkable invention by actually inventing this particular vulcanization process. Much improved chemical resistance, as I have explained. Water absorption capacity is lowered because your double bond now converted into the single bond because sulfur now connected with the carbons which are having the double bond. So when there is no double bond, definitely the your water absorption capacity would be lower. Water will not attack on the saturated or the single carbon. Okay. Better electrical insulation properties, like in ebonite, with better insulation properties would also be there in it. Okay. And has much lower elasticity, right? So it will have now the low elasticity. That means it will regain its position, regain its shape when you release the stretch. Okay. And then see, this is all about your natural rubber. So this is your natural rubber, and in the next class I'll continue with the synthetic rubber as well, right? So in the next class I will do all these things. So if you like the lecture, please give thumbs up to the lecture, and if you are watching video for the first time, please subscribe the Tetrahedron Chemistry classes and do share the channel with your friends as well. Okay, so that's it for today. Thank you very much.